Okay, so simple beam theory and properties of bone. So first, simple beam theory. What is simple beam theory? Generally, you know already what is a beam, so we'll not delve into this. However, what is simple beam theory? So when a beam is tried to be bended, imagine what is happening. Yes, let's imagine that this beam already get bended a bit. Yes, imagine what is happening with the structures of this beam, of the material. Yes, imagine what is happening with this part of the material and this part, this and this. You can see that all of the material gets into this spot. Yes, so here we have compressive forces. Yes, because we are compressing this top. But here the situation is different. Here we have tensile stress. Generally, most materials used in the engineering are far better in compression than in tension. For example, ceramcrete is far better in compression than in tension. It's far stronger in compression than in tension. And mostly, if something happens with the bridge, it's usually at the bottom, because here we have far higher tensile forces than everywhere else. And as you will learn, generally the structures are usually weaker when we have some tensile forces or shear stress. Yes, you already should know what the shear stress is. So this is first thing. What else I wanted to say? Oh, bones. So what about bones? Bones this would be a bone. What are the basic properties of the bones? Generally, wait a moment. Okay. Generally, bones are strong in compression, as I already pointed out, and far weaker in tension and shear stress. Yes, what is shear stress? The shear stress is generally a bit like rubbing the skin. Yes, so we have some material and we are acting on some layer of this material. For example, for the surface. Yes, so we have two surfaces in the same material, and those two surfaces are getting in different directions. It's like scissoring. Yes, and this scissoring is very hard to sustain by any structure, by any material. So the bone is strong in compression, but weak, relatively, of course, weak in tension and shear stress. This is important. What else is important? As any composites is anisotropic, so it is strong in, for example, compression top down, but far weaker in compression from the side. Yes, this is because the lamellas that are inside are not organized uniformly. They are organized mainly in the planes of the maximal loading. What else? How stiff is the bone is depending mainly on the age and size of the bone, obviously. In case of the children, the bone is far more elastic. It can bend even. So there is a possibility of the plastic deformation in case of the children. In case of the adults, it is not. In the case of the adults, it will just fracture. Also, when we have a fracture, in case of the bones, it's a fracture of the brittle type. Yes, so generally, if the bone would start to fracture, it usually fracture all the way through. Not always. In children it does not need to. There may be some microfractures, or even in adults, some fatigue fractures, for example, are the microfractures, and they does not need to propagate thanks to this lamellar structure of the bone. But if you would have some macrostructure, yes, macrofracture, so I mean something that could be potentially visible by naked eye, it would rather propagate through whole of the bone, at least in adults. Okay, what else is important? When you think about the beam theory, yes, you know already that most of the forces are applied on the surfaces, top and bottom. Why it's important now? It's important now because you know that in the center of such beam, theoretically speaking at least, there are no forces acting. Yes, because all of the forces, all of the strain is taken by the material near the surface. How we can apply this knowledge, how the evolution applied this knowledge, or God, it is applied in such a way then that the center of the structure can be empty. So the center of the bone are empty, and it does not reduces the ability to sustain bending, at least not much, but it reduces its weight. So such structure that is empty inside is a very good structure from the engineering point of view. Okay, I suppose it's enough for today. Thank you very much.